Hello, now we are going to look at how to graph quadratic functions. And a quadratic function is where we have a situation like this, where we have the output is equal to something squared plus x, so x squared plus some constant. If our highest power is x squared, that means we have a quadratic, assuming we don't have any unusual powers like x to the half or something like that. So this is the general form of a quadratic, and we're expected to know that form. It can come up in functions, it can come up in patterns. So we have to know that this is the general way of describing a quadratic pattern or quadratic function. As with any function, we can write it as f of x or g of x or h of x. Some function in terms of x is equal to, in this case, x squared minus 2x. So the fact that this is x squared and we don't have any unusual powers here means that this is a quadratic function. So the output of the function is the f of x. We input x into the function. That's what this means here. You input x into the function and it gives you the output according to this rule, according to this relationship between x and y. And when we're graphing these things, the output of the function will be our y coordinate. So if we want to graph this function in the domain, so our domain is our input values. So in this case, we're going to go from x is minus 1 up to x is 3. So x is greater than or equal to minus 1, x is less than or equal to 3. Now there's an infinite number of x values between those two points, between those two values of x. We just graph the whole number values of x in between, and then we're going to use what we know about the general shape of a quadratic to fill in the curve once we have those points to guide us. So our first point is going to be f of minus 1. X is our first column, then the function description is the middle column, and then the coordinates we're going to plot are the right-hand column. So our first x value is minus 1. So f of minus 1, when x is minus 1, that means you write down minus 1 anywhere there was an x, and we get 3. So we would write down minus 1, 3 for our first point, and I'm going to fill in the rest of the points in our table now. So now I've filled in my x values that I'm interested in from the domain I'm going to graph, and I get all of these points. Now it's important to remember the meaning of a function. When x is minus 1, y is 3. When x is 0, y is 0. These points meet this description, this relationship between the input value x and the output value y. That's what makes these points on the curve. They meet this description of the relationship between the x's and the y's. Now, when we're talking about a quadratic pattern or a quadratic relationship, the slope of this is not going to be the same all the time. So x is increasing by 1 each time along here. So we can look at how y is changing. So to go from 3 to 0, we would minus 3. To go from 0 to minus 1, we would minus 1. To go from minus 1 to 0, we would add 1. To go from 0 to 3, we would add 3. So the rate of change is very obviously not the same for our curve, and that makes sense because it's not a straight line, so that means that its rate of change is going to change all the time. But quadratic patterns do have something that's constant. We may be able to see that the rate of change of our rate of change is actually always the same. Going from minus 3 to minus 1, we add 2. Going from minus 1 to 1, we add 2. Going from 1 to 3, we add 2. So while the slope of the curve is not constant, the way the slope changes is, or to say it in terms of rates of change, the rate of change of the rate of change is constant. How quickly the slope changes is constant for a quadratic curve. And this is important for understanding quadratics in patterns, and it's good to think about when we're doing functions as well. So now we have our set of points, we can start to graph them. So if I go to my x and y axis here, my first point is at minus 1, 3. So I go from the origin, in the door minus 1, up the stairs 3, in the door 0, up the stairs 0. So I just stay at the origin. in the door 1, up the stair, or down the stairs -1. So in the door 1, down the stairs -1, in the door 2, up the stairs 0, and in the door 3, up the stairs 3. So those are the points that I've got. Now this is a curve. Very obviously this is not a straight line. So when I'm connecting my dots, I need to know that I'm dealing with a curve. I need to know the general shape of a quadratic to guide me as to how I fill in this curve now to connect these dots. So I'm going to draw that now. When I have this drawn in, I can see that I have a reasonably even curve going around my points. I am not drawing straight lines in between these points, so this is not coming down to some triangle. It's curving around through the points. So I need to know that that's the general shape of a quadratic curve. So now how can I use my quadratic curve to read information off? Well, what would be the output of the function when x is 3? So I'd say, well, x is supposed to be 3, and I'd show that I was getting my information from the graph by doing a dashed line here, and I would come across, I'd say, well, the y value, the coordinate of that point is going to be x is 3, y is 3. So that would be my point there. What would f of -1/2 be? Well, this is a little bit more awkward to read, but we can say that's about x is -1/2. So again, when the input of the function is -1/2 or -0.5, what should the output of the function be? So how high up should I be on my curve? So I go up vertically, and I say, well, what would be the y, what output of that? What would be the y coordinate there? Well, that's about a quarter, maybe a little less than a quarter, so maybe 0.2. So 1.02 or 1.025 would be about where I would say that my line dropped there ever so slightly. So about 1.25 or 1.2 would be what I would say would be the output of the function when x is -1/2. Now, what value of x would make the output of the function equal to 0? Well, the output of the function is the y value. So if we're looking for where y is 0, that means we must be sitting along the x-axis. So all of the points on the x-axis would have their y coordinate as 0. So I'm looking for where I cross the x-axis, and that is called the root of the function. Again, it's called the root of the function because if we think of the x-axis as ground level, where our function goes to ground would be the root of that function. So where does that happen? Where do we hit ground level? Where do we hit the x-axis on our red curve? Well, that happens when x is equal to 0 and when x is equal to 2. So 0, 0 and 2, 0 would be the coordinates of our roots, and x is 0 and x is 2 would be the x values that make that statement true. And we can also do this algebraically. We know what f of x is. The description of f of x, the rule for f of x, is x squared minus 2x, and that's supposed to equal 0. So we could also write that down, and we could use the minus b formula, or we could factorize to try and find the values of x that would make that true. So if we did it by factorizing, we'd have a common factor of x, and we'd take that out, and we'd say, well, I have two things multiplied together to give 0. So if x was equal to 0, that statement would be true. Or if x minus 2 was equal to 0, that statement would have to be true. So I could rearrange that equation to find the value of x that would make that true. And I would be left with x is equal to 2 and x is equal to 0 as the values of x that would make this statement true. And I can see that that works out the same as when I do it visually. Now, when I was drawing my graph, I made reference to the fact that we have to know the general shape of a quadratic curve to connect our dots properly. So the general shape of a quadratic curve is going to be a smiley face or a frowny face. And the way that we figure out which one it is the coefficient of the x squared, the number in front of x squared. So for the graph that we drew here, I've rewritten it here, f of x is equal to 1x squared minus 2x. I didn't bother writing down the 1 here. We often don't when it's a 1. But this is a plus 1. So it's a positive number in front of the x squared. So positive gives a smiley face. When we're positive, we're smiling. A negative number as the coefficient of x squared, the number in front of x squared, a negative number would give a frowny face, a sad face. When we are negative, we are frowning or sad face. So that's the general shape for connecting our dots for a quadratic curve. Now that we've drawn the curve, we want to understand a little bit more about its shape. We can start thinking about more detailed descriptions here. So if we have this question here, where's the minimum of f of x? Well, f of x is the output of the function. What is the lowest value? Minimum would mean the smallest to the lowest. What's the lowest output value of the function? Well, that means what's the lowest y value, and this happens down here. So what's the coordinates of that point? Coordinates of this point, the lowest point on our curve would be the minimum. That's going to happen at x is 1, y is minus 1. We can draw in our dashed lines to show that we are getting that from the graph. What would be the line of symmetry of f of x? Well, a line of symmetry is effectively a line that you could fold the shape over onto itself. So where could we do that? Well, if we folded this page along the blue dashed line here, we folded this graph along the blue dashed line here, it would fold over onto itself. The red curve would fold over onto itself. So this is the line of symmetry. It's the folding line or the mirror line for our curve. And that happens. What's the equation of that blue dashed line? Well, what's true of every point on that blue dashed line is that x, the x coordinate, would be equal to 1. So if we want to describe all the points on the blue dashed line, we just say the x coordinate has to equal 1. That's our description. Now, where is the f of x curve negative? So the output of the function has to be negative. So that means it's less than 0. And what is less than 0? The y output of the function has to be less than 0. Well, down here is where the function is negative. The output of the function, the y values for our coordinates would be negative. So in between where x is greater than 0 and where x is less than 2, that's where the outputs are going to be negative. And we can write that as a single sentence. We can say that x has to be greater than 0 or less than 2. And that's where the red curve has negative y coordinates, where its output is negative. Now, where is f of x increasing? Well, increasing means something is going up. It's getting bigger. So where is it getting bigger? Well, past the minimum point here, the curve is rising. Its slope or its rate of change is positive. It's getting bigger. So that means that when x is greater than 1, we are going to have the function increasing, the slope or the rate of change being positive. The curve is going upward rather than downward. Now we can also look at modifications to our f of x curve or any quadratic curve. If we had the function g of x and we're going to say it's twice the output of the f of x function, that would be 2 times x squared minus 2x. So the g of x function is going to be 2x squared minus 4x. So the g of x function is double the f of x function. So what would that look like when we graphed it? I'm going to draw that now. Now when we draw that in, we draw g of x in with our blue curve here. It's my g of x curve. What can I see about it? What's the relationship between g of x and f of x? Well, when x was 3 on f of x on my red curve, y was 3. And now when x is 3 on my blue curve, y is 6. When x was 1 on my red curve, y was minus 1. When x is 1 on my blue curve, it's minus 2. Y is minus 2. What's happened by multiplying the output of the function by 2 is perhaps predictably, all of the y values have been doubled. So for a given x value, I'm twice as far away from the x-axis. So that makes the function look like it's been stretched up and down by being multiplied by 2. But the roots haven't been affected. I'm still going through x is 0 and x is 2 for the roots of the function because 2 times 0 is still 0. So multiplying my function by a number stretches it out, but it doesn't affect the roots. And that is what we need for now.